So hi everyone, in this video we are going to solve this particular problem on GFG. The name of the problem is max sum subarray of size k. So we'll be given an array of integer that is denoted by ARR and a number k. Return the maximum sum of the subarray of size k. So we'll be given an array. Let's see this example, the first one. Let's take a screenshot of that and see this as an example. So we'll be given an array like this as the first one in the example, and we'll be given an integer that will be denoted by k. So what do we need to do? We need to find the maximum sum of the subarray that is of size k. So we need to take each and every subarray of size k and we need to find the maximum out of them. So a subarray of size k would be 100 and 200. Another subarray could be one that would be this 200 and 300. This will form a subarray. This 300 and 400 will form a subarray. So out of this three subarray, we need to find which one is the which one will sum up to give us a maximum sum. So this will give us a sum of 700. This second one will give us a total sum of 500. This one will give us a total sum of 300. So out of these three, we can see clearly the last one is the bigger one. Like it will give us the maximum sum for a subarray of size 2. Similarly, for this example, if we see if k is 4, then we need to take subarrays of size 4. So the first subarray would be this one over here. So the sum of this subarray will be 5, 10, 15, 17. So the sum will be 17. Then the next 4 subarray, like the next 4 element will sum up to be 23, 25, 35, 39. Then the next 4 will give us a total sum of 38. Then the next 4 will give us a total sum of 10, 33, 36, 37. Then the next subarray of size 4, that is this one over here. This will give us a sum of 26, 27. Then the next one, that is this one will give us a total sum of 24. So this will give us a sum of 24. Yeah. So out of this subarray sum, which one is the maximum one? The maximum one is the one that is giving us a sum of 39. That is the second one. Yeah. So 4 to 6, 16, 29, 39. Yeah. So this is going to be the maximum one, and that is the output. So yeah, one way to solve this is by doing exactly the same thing that we did for our example, is by going over the array and calculating the sum of each of the subarray. So suppose if we take the first example over here, 100, 200, 300 and 400, then we'll be going to each and every index and we'll be counting the sum of the next k element. So if k is 2, then we will be counting the sum of the next two element. Similarly for this one we will be counting the sum of next two elements. Similarly for this one we will count the sum of this two element, and whichever will give us the maximum sum, we will be saying that that is our answer. Then what is going to be the time complexity of this approach? For each of the element we need to go to the next k element. So if we iterate over each and every element, that will be of big O of n, and for each of the element we are going to check for the next k element. So it will be big O of n cross k. That is going to be the time complexity. And since we are not using any additional space, so the space complexity will be big O of 1. That is constant space complexity. So if we see the constraints, then the size could go up to 10 to the 6 and k could go up to as big as the array size. So it will also go till 10 to the 6 at the worst case. So this big O of n cross k can be as big as big O of 10 to the 6 multiplied by 10 to the 6. That is big O of 10 to the 12. That is definitely greater than 10 to the 8. So it will not pass all the test cases. So since it will not pass all the test cases, we need to find an optimal way so that it pass all the test cases and the solution gets accepted. So to do that, what we need to do, we need to optimize it. So instead of going to each and every element and searching for the next k element, what we can do, we can maintain a window of size k starting from the first index, and as we go to the right side, what we'll do, we will keep reducing the window size by eliminating the first element and taking the next element. So the new window will be this one. Similarly, when we will go to the next element, we will eliminate the last one that is there. By last one I mean the first one that was assigned to the window. So here the first one is 200 that was assigned to this window, and then 300 came, so we'll be popping out 200, and then we will create a new window and then take the 400 in the exact same window that we have previously created. So that way we don't have to just go through the next k element. We'll keep track of all the next k element by summing up all the element that is present in the window. Similarly, if we see that for this example, then we'll be able to understand it better. Suppose these are the element 1, 4, 2, 10, 23, 3, 1, 0, 20. So suppose k is 4, then we'll keep track of a window that is of size 4. So we'll be creating a window like this, and then we'll be saying what is the sum of all the element that is present inside window. That is 5, 7, and 17. So we'll be saying okay, the sum is 17. Then what we'll do, we will take this window, we will eliminate this element that is there in the very left side of the window, and we'll add the element that is just right to the window. So the sum will be 17 plus 23, that will sum up to 40, and we'll eliminate this element, the first one. So since we will be eliminating this one, so this will be subtracted and we'll be getting 39. Now we'll check if 39 is the maximum sum that we can get. If that is the case, then we'll return 39 in the end. Otherwise, we'll do the same thing for the other element. So we'll be eliminating 4, we'll be subtracting 4, we'll be taking the next element and add this to the result. So it will be 35, and we'll be adding 4, not 4, we'll be adding 3, this one element. So it will give us 38. Yeah, this one will give 38, right? Yeah, here we have written 38. So again we'll eliminate the leftmost element from the window, and we'll be adding the right element that is present after the window. So we'll be adding the sum 48, and we'll be eliminating which element? We'll be eliminating 2, right? So we'll be subtracting 2 from 48, which will be 46. We got 46? No, I don't think we got 46 anywhere in the area. Ten, 23, 3. Okay, this should be 1. So we'll be adding 1, not 10. Okay, we'll be adding 1 over here, not 10. So 31, 38 plus 1, it will be 39. And we'll be subtracting 2, that will give us 37. Again we'll do the same, like we'll be adding 0 in the window, and we'll be subtracting 10. That will give us 27. Again we'll be adding 20, and we'll be subtracting 1. Not 1, 23. So we'll be subtracting 23, that will give us 4, and we'll be adding this 20, that will give us 24. So that's how we'll be maintaining a window that will keep sliding to its right. That's why it is called sliding window. And since we'll be just iterating over the array, so the complexity will be big of, at the beginning we need to take the k element, like all the k element in the window. So for that we need to iterate once, and we need to go through each and every element. So for that, let's say this can go up to n time. So the time complexity will be big of k plus n, which will be big of 10 to the 6 at the worst case. So this is definitely less than 10 to the power 8. So the time complexity is pretty much optimized, we can say. And the space complexity will be, like we'll be maintaining a window, let's say. So if we maintain a window of size k, then the space complexity will be big of k. But instead of maintaining a window or queue, we can maintain two pointer to point to the left and right of the window. That will also work fine. So in that case, the space complexity will be turns out to big of 1, that is constant. So that will give us the most optimized answer. So let's code it up to understand it in a better way. So we need to keep track of the left and right index of the window. So let's say the size of the array is n, and let's say the index of the window will start from 0, and for now let's say the right index is also 0. So what we'll do, we'll take k element and we'll add that in the window, and we'll say that the window sum is the sum that will keep increasing by taking the sum of the next element and by deducting the sum of the left element. So first we need to go to each and every element. So let's say we are at the first index, like we are at the 0th index, which is the first element. Then we are going to add that to the window sum. And at each step we are going to increase our r by 1. And now what we are going to do, we are going to check if this window has a size which is greater than k or greater than or equal to k. So how we are going to do that? We are going to check if r minus l is greater than equal to k. Then what we are going to do, we are going to say that okay, this is a window sum and it has a size that is greater than or equal to k. So we can say that okay, this is a valid window and we can compare it with our answer. So we'll be assigning 0 to answer just to get the maximum. We need the maximum, right? So we are putting a very less value to our answer, so that whenever we get a value that is greater than answer, we can update it immediately. So if window sum is greater than answer, then we'll be updating our answer with the current window sum. And suppose a window is exceeding the limit of size k, then what we should do? Then we should deduct the element that is present in the left index. So left index starts from 0, so we can say that we're subtracting the value of the left index so that it will get deducted from the window, or it will be popped out from the window. If we're maintaining a queue, then we would be using the term popping out. But since we are not using a queue, we have to do it by using the index. So let's say if r minus l is greater than k, then we are going to take the leftmost element that is present in the window, and we are going to deduct that from the window sum. And since after that we are going to take the next element as the leftmost index, so we need to increase the L pointer by 1. So at this time we can say that this is definitely going to be equal to k, because we have handled this case separately. So if that is the case, then only update the answer. Yeah, this looks good to me. Let's see if it is passing the test case or not. Yeah, it is giving the correct output for the example test case. Let's see if it is passing all the test cases. Yeah, it is passing all the test cases. So this was the most optimized approach that we could come up with.